Hi, I'm Professor Kelly, and this is a lecture on currying for CSCI 308, Programming Language Design. By currying, I don't mean making a delicious dish. I mean a mathematical trick for representing functions. Learning goals for this lecture are to explain anonymous functions in currying, to implement higher-order functions in Haskell, and to apply the function composition operator. The famous Church-TURING thesis defines computability. A function is computable if and only if it can be computed by a Turing machine, which was proposed by Alan Turing in 1936, or by lambda calculus, which was proposed by Alonzo Church, also in 1936. Because Alonzo Church and Alan Turing both independently came up with mathematically equivalent formalisms for defining computability, the Church-Turing thesis credits both of their names. If machine instructions to a Turing machine is the basis of imperative languages such as C++, then mathematical descriptions in lambda calculus is the basis of functional languages such as Haskell. Instead of describing a set of instructions to a machine, we are describing a set of mathematical functions. The foundation of lambda calculus is anonymous functions. Take f of x equals x squared plus 2. This can be represented in lambda calculus as an anonymous function lambda x dot x squared plus 2. The function no longer has a name. We simply specify that it takes an x, and the result is x squared plus 2. In Haskell, this can be represented as slash x arrow x squared plus 2. The slash represents the lambda symbol. There's no lambda on the keyboard. Slash will have to do. We can apply an anonymous function in Haskell by putting brackets around it and then putting the arguments after the brackets. Our anonymous function and the argument 3 results in 11. 3 is bound to x. 3 squared is 9. 9 plus 2 is 11. When we name a function in Haskell, such as giving this function the name foo, we're still using anonymous functions. A call to foo of 3 is actually a call to the anonymous function. We then apply the anonymous function to 3 and get 11. A call of foo to 3 is going to be replacing both foos with an anonymous function to get 123. The first foo gets us 11. The second foo then takes 11, squares it, and adds 2 to get 123. There are several things about Haskell that may have struck you as mysterious. Why does Haskell not use brackets for function calls? For example, why would you say foo 6.3 with no brackets rather than foo 6 and 3 in brackets with a comma separating them, like in most other languages? Why do Haskell type signatures not distinguish between parameters and return values? You'll often see type signatures like this, foo, int, maps to int, maps to int, which seems to put return values and parameters on the same playing field. Whereas you'd expect the parameters to be in some sense separate from the return values. For that matter, can lambda calculus represent functions with more than one parameter? The answer to all these questions is currying. Currying is a mathematical trick for decomposing functions with multiple parameters into functions with only one parameter. This was invented by the mathematician Haskell Brooks Curry, who gives it its name. Haskell Brooks Curry is, of course, the namesake of the Haskell language as well. Take, for example, the function abc equals a to the power of b plus c. This can be represented as lambda calculus. Using currying, we are representing this function as a series of functions. To do x equals f of a, b, c, we first create a function g that takes a and returns another function called h. We then pass b into h, which returns another function called r. R then takes the last parameter, c, and returns x. Let's see this in action. Suppose we have foo x, y, z equals x to the power of y plus c. When we call foo of 6, 2, 3 and get 39, that is to say, 6 squared is 36 plus 3 is 39, what Haskell is actually doing behind the scenes is it's replacing foo with this complicated-looking anonymous function. This function simply takes one argument. That argument is x. Haskell just looks to the left of the anonymous function in search of that one argument. It binds 6 to x and returns another function. This function takes y and then maps to z, which then maps to 6 to the power of y plus z. We can now apply this function to the next argument, which is 2. We bind 2 to y, substituting the 6 to the power of y with 6 to the power of 2, and returning a function, z maps to 6 to the power of 2 plus z. We can now apply this function to the last argument. We bind 3 to z, substituting z with 3. We get 6 to the power of 2 plus 3. We can now solve for 39. So why does Haskell not use brackets for function calls? Haskell functions only actually take one argument. You don't need brackets to indicate what is and isn't an argument. Haskell will always just look to the right of the function if the function requires an argument. Foo of 6, 2, 3 is actually foo of 6, which then returns a function that takes 2, and that returns a function which takes the 3. Why does Haskell type signatures not distinguish between parameters and return values? Well, we told you that the last value in the type signature is the return value. That was, strictly speaking, not true. The last value is the ultimate return value, but is not actually the return value. The return value is everything after the first arrow. Properly speaking, Haskell functions are returning the whole part that is after the very first arrow, which is going to be a function in the case where there are more than one argument. Higher order functions are functions on functions. Strictly speaking, basically all functions in Haskell are higher order functions because functions in Haskell are curried and return functions. We're going to define higher order functions a bit more narrowly than that, though. We're going to say that functions that take functions as arguments or return functions as their ultimate return value are higher order functions. Take, for example, high. High takes as an argument a function a to b and returns a function a to b. You can already tell that this is a completely pointless function. Another way of thinking about it, however, is it takes a function a to b and an argument of the type a and returns a return value of type b. The function is called fun, the argument is called arg, and the function is defined as returning fun arg. We can see how pointless this function is in action. We can call high on head and 1, 2, 3. High will apply head to 1, 2, 3, and we get 1, because the head of the list 1, 2, 3 is 1. This function may be redundant, but it illustrates the principle of how to create higher-order functions, which is an extremely powerful capacity of Haskell. Consider function composition. Suppose we want to have a function that just takes whatever number and multiplies it by 3. For example, let's apply this function multiply by 3 to the number 2. 2 times 3 is 6. Suppose we have another function called add4 that just takes whatever number and adds 4 to it. So if we multiply by 3 and then add 4, 2 times 3 is 6. 6 plus 4 is 10. What if we wanted to compose these two functions, combining them into one function? Haskell is an operator that lets you do that. It's represented by period. Add 4, period, multiply by 3, composes the two functions into one function. It first applies the multiply by 3 function and then applies add 4 to the result. So add 4 dot multiply by 3, 2, is going to first multiply 2 by 3 to get 6 and then add 4 to get 10. If we reverse the order, it would add 4 first. 2 plus 4 is still 6, but then we multiply by 3 to get 18. The function composition operator is itself a higher order function. It takes two functions, composes them, and returns the composed function. We can use this operator inside of our functions. Math is not itself a higher order function, but it uses the function composition operator. It maps from an integer to an integer. It takes that integer and, using function composition, calls multiply by 3 and add 4. Math 2, 2 times 3 is 6, add 4, 10. We can, however, define a higher order function to do this. Both funds is a higher order function. Both funds doesn't take any arguments. Instead, it returns a function that maps from integer to integer. Both funds is defined as add 4 dot multiply by 3. Essentially, it is an alias for the same function. Both funds 2 returns 10. Learning goals were to explain anonymous functions in currying. All functions in Haskell are anonymous functions that use currying to take one argument and return a function that takes the remaining arguments. Our second learning goal was to implement higher-order functions in Haskell. Higher-order functions take functions as arguments or return functions, and they are pretty straightforward to implement in Haskell. And apply the function composition operator. The function composition operator is represented by dot. For example, g.f(x) applies f to x, then applies g to the return value of f.